Hello, good morning. My name is IBM, and today I would like to welcome you to Electric Fields Solve the Past Paper Questions, Part 4. Today we shall go into what was called Electric Fields 2 in the old curriculum. So today we shall move to more advanced questions rather than the ones that we have been seeing in a uniform field. Today we shall get an opportunity to get to see questions for about electric fields in a non-uniform electric fields or due to point charges. And so today we shall be able to solve them and learn how to deal with such questions. So straight away we shall move to our document. We shall move to our document. So we are now on this document, and I'll try to expand it so that it can fill maybe the page. So today we are on electric fields. So you pull out your document for the past paper questions, and you scroll. We are still on electric fields, so I'll look for page 61. So we are here on electric fields, but we had finished the part of uniform electric field. And today I want us to concentrate on non-uniform electric fields or electric field due to point charges. All these parts we're done. Okay, so we were supposed to start from this page, I think page 88. So let's begin. I'll select a pen and I'll make this to be a little bit thinner. I'll use blue. So state an expression for the electric field strength in terms of E, distance R, point charge Q in a vacuum. State the name of any other symbol used. So earlier on in the lessons, we already established that electric field strength E is equal to Q divided by 4 pi epsilon naught R squared or X squared. Many would prefer to use X. So electric field is going to be given as epsilon naught, say X squared. Now the only symbol here, they said R, using R, so this will be R squared, not X, not epsilon. Not X squared, so this will be R squared. So the only symbol here that we can do, of course we can't explain 4 pi, but we can explain epsilon naught. And epsilon naught is the permittivity of free space. Permittivity of free space. So for such a question, avoid writing E as equal to KQ over R squared, because again it means you will have to define K. So you will have to tell the examiner that K is 1 over 4 pi epsilon naught, and again you go ahead and explain epsilon naught. So instead of doing all this, you would rather state the equation the way you know it, including this constant 1 over 4 pi epsilon naught, and you just explain the permittivity of free space or permittivity of a vacuum. Part B. 2-point charges A and B are situated at distance 10.0 centimeters apart in a vacuum, as shown here. A point P lies on the line joining the charges A and B. Point P is distance x from A. The variation with the distance x of the electric field strength E at point P is now shown here. So this is the variation. So we can first of all see that this is along this, I think it's along here, and this is This is here in the middle. State and explain whether the charges A and B have the same or opposite signs. Note that it is a graph of E against X. If we know that for like charges, the value of, if we had like charges, say we have charge A and charge B are like charges, there would be a point between them where the resultant force is 0. And at that point where the resultant force is 0, the value of E becomes 0. When you look at the graph, there is no point where it is showing that the electric field strength became 0. What does that mean? It means A and B cannot be like charges. If they are like charges, there is a neutral point between them, which means at the neutral point, the force is 0 and the electric field strength at that point is 0. Therefore, these are not going to be like charges because there is no such a point where E becomes 0. So we can say these have opposite signs. They are not like they don't have like signs, so they have opposite signs. They have opposite signs. Reason: the field does not change direction. The field does not become 0. The field does not change direction. Or we can simply say the field does not become 0. The field does not become 0 between the charges. So if the field would become 0 between the charges by the graph, if the graph was touching the 0 axis of the vertical, then we would conclude that actually there is a point between the charges where the field becomes 0, the field strength is 0. So these would be like charges. But since there is no such a point, then we say they are unlike charges, they have opposite signs. Okay. State and explain whether the charges A and B have the same or different magnitudes. They have the same or different magnitudes. And how do we see that? So to see whether they have the same or different magnitudes, we look for the minimum where the minimum field strength is. So let's see, the minimum field strength is here. I think this is 5. Note that the distance between the two charges was 10 centimeters and 5 is the midpoint. If the minimum field strength is at exactly the center of the two charges, then they have the same magnitude of charge. If the minimum was to be closer to B, then it would mean B has a smaller magnitude than A. If the minimum was to be closer to A, then it would mean that A has a smaller magnitude of charge than B. Because for like charges, the neutral point is closer to the weakest charge. But in this case, the minimum field strength is at the center between the two charges, so we can conclude that they have the same magnitude. They have the same magnitude. The reason is that the minimum field strength is at the midpoint. Is at the midpoint between the charges. The minimum field strength is at the midpoint between the charges. So please, it's better you print this if you want to learn very well. Have this document in hard copy so that you can follow the lessons on a hard copy. An electron is situated at point P. Without calculation, state and explain the variation in the magnitude of acceleration. of the electron as it moves from the position where x is 3 centimeters to the position where x is 7 centimeters. So we go to the graph. The position where x is 3 centimeters, I think it's around here in the middle. X 3 centimeters is around here. Then to the position where x is 7 centimeters, I think 7 centimeters is in the middle here. 7 centimeters is around here. So we are going to explain the magnitude of the acceleration of an electron which is placed at a point where x is 3 centimeters until we reach a point where x is 7 centimeters. First of all, I want you to note that electric field strength E is defined as the force acting on a unit positive charge. So in other words, electric field strength is equal to Ma over the charge. So it means the field strength E is directly proportional to the acceleration. The field strength is directly proportional to the acceleration. When E decreases, it means the magnitude of force is decreasing. And because force is mass times acceleration, it also means that the acceleration is decreasing. At 5 centimeters here, where E is minimum, it means the force is minimum. And that also means the acceleration will be minimum. After 5 centimeters, as we move to 7 centimeters, the electric field strength is increasing, which means the force is also increasing, which means the acceleration is also increasing. So you just need to note that force is directly proportional to electric field strength, and it means, and since force is mass times acceleration, it also means that the acceleration is directly proportional to the electric field strength. So we are saying between x equals to 3 to x equals to 5, electric field strength is decreasing, which means the force is decreasing, which means the acceleration is decreasing. It is going to be minimum at 5 centimeters because the electric field strength is minimum at 5 centimeters. Then after 5 centimeters, the value of E is increasing, which means the force is increasing, and therefore the acceleration is increasing. Okay, so we can now put this in words. We can put this in words. So the force F, we know that the force is going to be the charge times the electric field strength. Or E is force over charge. And we also know that the force is equal to the mass times the acceleration. So what does that mean? The force is directly proportional to E, and if force is directly proportional to E and F is equal to ma, so we can say that acceleration. So the acceleration is proportional to the field strength. The acceleration is proportional to the field strength E. So from x equals to 3 up to x equals to 5.0 centimeters. From the graph, we have seen that the field strength decreases, so the acceleration decreases. And it is minimum at x equals to 5.0 centimeters. Then from x equals to 5.0 centimeters up to x equals to 7.0 centimeters. From the graph, we have seen that the electric field strength increases. So we just simply say acceleration increases. Acceleration increases. Okay, another question. Define what is meant by electric potential at a point. We know that electric potential is the work done per unit charge. The work done per unit charge in moving a positive charge from infinity to the point. So to define electric potential, we need to imagine moving a unit positive charge from infinity to a certain point. The work done in moving a unit positive charge, because this is electric fields, so it is going to we are going to be referred to positive charge. The work done per unit charge in moving a positive charge from infinity to the point is what we call the electric potential. In an alpha particle scattering experiment, which you must have studied in AS, alpha particles are directed towards a thin gold foil, a thin film of gold as shown here. The apparatus is in a vacuum. The gold 197 nuclei in the film may be considered to be fixed point charges. The alpha particles emitted from the source each have this energy, 4.8 mega electron volts. Calculate the initial kinetic energy in joules of the alpha particle. So we first convert this, we just convert this. 4.8 mega is times 10 power 6, and from 1 electron volt is 1.6 times 10 power negative 19. So this will be times 1.6 times 10 power negative 19. Then I press my calculator. So this is giving me 7.7 times 10 power negative 13. This is mega, this is electron volts. 1 electron volt is 1.6 times 10 power negative 19 joules. So this is now in joules. Next, the distance d of closest approach. Excuse me. So the distance d of closest approach, I don't know, this space is very small, but I'm going to find a way. So at least we have the kinetic energy of the molecules. We have the kinetic energy. Actually, here the exact value that I got was 7.68 times 10 power negative 13. I just rounded off to two significant figures. Avoid answers which are not exact. Avoid writing answers which are not exact to less than two significant figures. Avoid writing answers which are not exact to less than two significant figures unless it is uncertainties in AS. So we want to find the distance of closest approach. But we know that as the alpha particle approaches the gold nucleus, it loses its kinetic energy. Therefore, as it loses kinetic energy, because they are both positively charged, it gains potential energy. So we can assume that the loss in kinetic energy of the alpha particle is the same as the gain in potential energy. But yet we know that potential energy is given by Q, charge times potential, which is Q times small q over 4 pi times epsilon naught times the distance between the two particles. Potential energy is going to be the small charge times the potential, where potential V is given by Q divided by 4 pi epsilon naught times d. So potential energy is Q small q over 4 pi epsilon naught d, and therefore we are just going to equate our energy there, which is 7.68 times 10 power negative 13, to be equal to Q for gold is 197.79. The charge of gold is 79 E. An alpha particle is a helium nucleus, He42. So the charge here is 2E. So it means when I substitute here, I'll have 79 for the gold times 2 for the alpha, then times E, which is 1.6 times 10 power negative 19, and this will be squared because it is 79E times 2E. Then this is divided by 4 pi epsilon is 8.85 times 10 power negative 12, then times d. Alternatively, we would just use k, which is 8.99 times 10 power 9 instead of 1 over 4 pi epsilon naught, because the charges are placed in the vacuum. You would just replace 1 over 4 pi epsilon naught with that quantity there. I'm just pressing the calculator because I don't have space. I'm pressing the calculator to find D. So you just cross multiply, make D the subject. Me, I'm just putting it in the calculator. So my calculator is giving me 4.7 times 10 power negative 14 meters. You can also verify. Know that this is 19, not 9. I hope you can see this. This is 19. Use your answer in B to comment on the possible diameter of a gold nucleus. Because this is the distance, this is how close the alpha particle comes to the gold nucleus, then I can predict. Even if I say this is the distance between the two centers, then it means the radius or the diameter of the gold nucleus must either be equal to this or less than this. So the diameter must be less or equal to the diameter must be less than or equal to 10 power negative 14 meters. It must be less or equal to 10 power negative 14 meters, or another value close to this. It can also be 10 power negative 13 meters. And of course, we have theory from AS that the diameter of we have theory at the back of our mind that the diameter of a gold nucleus is actually, or the diameter of a nucleus is approximately 10 power negative 14 meters. The diameter of an atom is approximately 10 power negative 10. So at least we have the theory at the back of our minds. Next, so when they said comment, this is my comment. The diameter must be less than or equal to 10 power negative 14 if this is how close the gold nucleus and the alpha particle can come. So the diameter must be less. State one similarity and one difference. State one similarity and one difference between the fields of force produced by an isolated point charge and an isolated point mass. So note, from what we have already seen in gravitation, if we have an isolated point mass, we know that the field lines are radial and they terminate towards, they move towards the towards the what? Towards the mass. This is if I'm considering the mass. If I'm considering a charge, let's say it is positively charged or negatively charged, the field lines are also radial. But here they did not specify the charge, the sign of the charge. So the field lines are also radial, but here they can be towards, if it is a positive charge, they can be away from the charge. If it is a negative charge, the field lines could be terminating towards the charge. So for the fields, for a point charge, the field lines can either be away from the charge or towards the charge. But in all cases, you see that both field lines are radial. So we can say both fields are radial. In other words, they both have an inverse square variation. Both have the inverse square variation. Both fields are radial, or it means both have inverse square variations. As we move away from the mass or the charge, the field strength reduces as an inverse square. That's what it means. Both fields are radial, but for the difference, we know that those of masses are always towards the mass. Both those of the masses are always towards the mass, but those of the charge can be towards or away from the charge depending on the sign of the charge. So direction is always towards the mass. Direction is always towards the mass, and for for a charge, it can be towards or away from the charge. This one is towards the mass. This can be towards or away from the charge. So that is the difference. Field lines on the charge can be directed towards the charge if the charge is negative, or away from the charge if the charge is positive. Yet in gravitation, for a mass, the field lines are always towards the mass. An isolated metal sphere A of radius r has the charge positive q, as illustrated. At P, a point P is distance 2r from the surface of the sphere, so that means the total distance between P to the radius is 3r. Determine an expression that includes the terms r and q for the electric field strength E at point P. Note that we defined E as the force acting on a unit positive charge, so E is going to be Q divided by 4 pi epsilon naught times x squared, but x is going to be 3r. So it means E is going to be Q divided by 4 pi epsilon naught, where there is x, I'm putting there 3r, and this is squared. So this is going to be Q over 4 pi epsilon naught times 9r squared when you open that bracket. So the answer we need here is going to be Q divided by 36 pi epsilon naught r squared. So that will be the expression required. In part C, a second identical solid metal sphere B is now placed near sphere A. The centers of the spheres are separated by the distance 6r, as shown here. Point P lies midway, so that means the distance from P to this one is 3r, and the distance from P to the other one is also 3r, if that is midway. Sphere B has a charge, negative q, Explain why the magnitude of the electric field strength at P is given by the sum of the magnitudes of the field strengths due to each sphere. Explain why the magnitude of the electric field strength is given by the sum of the magnitude of the field strength of each sphere. Note that to define electric field strength, we imagine a unit positive charge placed at point P. Sphere A is going to repel it because it's positive. So the electric field strength due to A is going to be in that direction. Sphere A repels our positive charge. To define electric field strength at a point, we imagine a unit positive charge placed there. So we are imagining a charge of 1 coulomb placed at P. It is positive. So because it is positive and sphere A is also positive, it is repelled to the right. Sphere B is negative. So our positive charge here is going to be attracted in that direction. So this is the direction of the electric field strength due to sphere B. So you notice that these are in the same direction. Therefore, to find the resultant electric field strength on a positive charge at P, it will be simply the sum because the electric fields are in the same direction. Therefore, we shall simply say that fields due to each sphere are in the same direction. Fields due to each sphere are in the same direction. Okay, again, explain why the electric field strength at point P due to the charged metal sphere is not, in practice, going to be equal to twice E. Explain why the electric field strength at point P due to the charged metal sphere is not, in practice, equal to 2E, where E is the electric field strength we determined in B. So we are saying the electric field strength here is going to be the sum of these two values. When we had only one charge, the electric field strength was given by this. This was E. Now they want us to explain why we cannot predict that because for this one it was E, the distance has not changed, it's 3R. Then for this one would also be um, uh, E, so that the total electric field strength at P becomes twice E. Now, the electric field strength due to sphere A is E only if it is only sphere A around. Because if these two spheres are close to each other, then sphere A or sphere B cannot be considered to be isolated spheres. So they cannot be considered to be point charges. Therefore, the electric field strength at point P is also influenced by the presence of sphere B. So we can't say that sphere A or sphere B are point charges, even though you could see that the distance 6r is not so many times greater than the radius or the distance, the radius of each of these spheres. So it means there's a possibility that charges on sphere A can still experience a force due to charges on sphere B because they are relatively close. The charges on each sphere can affect each other. Even the charge distribution on each of these spheres can distort or can be distorted by the charge distribution on the other sphere because they are relatively close, so they are not considered to be point charges. Okay, so we are saying the charges on the spheres can still attract or affect each other since the spheres are still close. The charges on spheres, since one was positive, one was negative, I can say can attract or in general affect each other. So the spheres are not point charges. They are not point charges at their center. Because they are very close, we cannot consider them to be point charges. Note that every time you use the expression above, you must have considered these charges to be point charges. Also, you could think about how charges behave. Like I have said, charges on the surface of the spheres will move because once because of the effect. In other words, they are actually affecting each other. So we can say charge on the surface of the spheres move. So spheres are not going to be point charges at their center. So charges, the spheres are not point charges at their centers. Because they are close enough, charges on the surface of each sphere would move due to the effect caused by the charges on the surface of the other sphere. So they are no longer point charges. So we cannot think of E being equal to Q over 4 pi epsilon naught x squared or r squared if the charges are not point charges. Two charges are going to be considered to be point charges if their separation is far, far greater than the radius of each of them. Two spherical charges will be considered point charges if their separation is far, far greater than the distance between them. If the separation is very small, it means the charges on one sphere affects the charges on the other sphere. So this equation cannot work. Therefore, we cannot predict that the total electric field strength at point P will be just twice E, not at all. Okay, next. A metal sphere of radius r is isolated in space. Point P is a distance x from the center of the sphere as illustrated here. The variation with distance x of the electric field strength E due to the charge on the sphere is shown. So we have the variation here. This is at the center. All we need to know is the scale. The scale I think is 0.2, 4.2, 4.4, 4.5. That is 4.5 here in the middle. So let's see the first question. The first question is state what is meant by electric field strength. Remember, to define electric field strength, we imagine a unit positive charge. The force per unit charge acting on a positive charge is what we call electric field strength. The force per unit charge acting on a positive charge. The force per unit charge acting on a positive charge is what we call the electric field strength. Use the figure to determine the radius of the sphere and explain your answer. Of course, I've already determined the radius. The radius must be 4.5. Explanation, electric field inside the conductor or inside the sphere is going to be 0, or the potential is going to be constant. So there is no electric field inside a conductor, no electric field inside a conductor or inside a sphere, inside the sphere. So the radius is going to be 4.5. When we see that there is an electric field, then it means we are either on the surface or we are away from the conductor. Charges reside just on the surface. So there is no electric field inside the sphere. So that's why you see here there's a horizontal line to show that inside E is 0. And at the surface, there's an electric field which depends on the radius. That's why I'm saying the radius is 4.5 from the graph. So the answer there is 4.5. Use the figure to determine the charge on the sphere. Now that we know the radius, and we know that electric field strength is equal to Q divided by 4 pi epsilon naught x squared or r squared. We shall now know that Q is going to be E times 4 pi epsilon naught x squared. We substitute. We are going to read a value for E on the surface, and the value for E on the surface is the scale here is 5 divided by 10, 0.5, 1, 2, 3, 4, 5, 6. 6 times 0.5, 6 times 0.5, that is 3. We add to 15, it becomes 18. So electric field strength is 18 times 10 power 5, then times 4 pi, times epsilon, which is 8.85, times 10 power negative 12, then times x, which is the radius, that is 4.5, times 10 power negative 2 to change it to meters, and then it is squared. I will just press my calculator. So from my calculator, I am arriving at 4.1 times 10 power negative 7. An alpha particle is situated a distance 8 centimeters from the center of the sphere. Calculate the acceleration of the alpha particle. So we want at 8.0 centimeters, what is the value of E? 8.0, let's check. At 8.0, we are somewhere here in the middle. We are here in the middle of the box. At 8.0, we are in the middle of the box. So if the scale is 0.5, so plus 1.5 boxes. I don't know why it is hard to put that box up. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11.5. So 11.5 times my scale 0.5. That is 5.75. So it means E is 5.75. E is 5.75 times 10 power 5 volts per meter. That is the value of E at 8 centimeters. We want acceleration. We know that force is equal to Q times E, and we know that force is M times A. I mean MA. So it means the acceleration is going to be Q times E divided by M. I'm just combining these two expressions. So I'm substituting. It is an alpha particle, so the charge is 2e. For an alpha particle, the charge is 2e, so I will say 2 times 1.6 times 10 power negative 19 times the electric field strength at that point, 5.75 times 10 power 5, divided by the mass of an alpha particle. The mass of an alpha particle is 4u, where u is, this is 4 times 1.66 times 10 power negative 27. That is the constant, which is the atomic mass unit. So this will be 4 times 1.66 times 10 power negative 27. So we press the calculator. So from my calculator, I'm finding the acceleration as 2.8 times 10 power 13, two significant figures. Next, two positively charged identical metal spheres A and B have their centers separated by a distance of 24 centimeters. The variation with the distance x from the center of A of the electric field strength E due to the two spheres along the line joining their centers is represented in the figure. So here we have variation of E against distance. Variation of E against the distance. I will try to reduce this so that it fits on one page. So first of all, the first question is telling us to set the radius of the two spheres. So inside the conductor, E is 0. So you see here the line is along the x-axis. Here E is 0. So this is most likely the radius of that one. Here along the x-axis towards 24, E is 0. So between 22 and 24, E is 0. So that means this is also, the radius is also 2. So E is equal to 0 inside the sphere, or inside the spheres. So the radius is going to be 2.0 from the graph. The radius is 2.0. After 2.0, we see that E ceases to be 0 for the two spheres. Then number 2, the charge on the sphere A is 3.6 times 10 power negative 19. Determine the charge QB on sphere B. Assume that the spheres A and B can be treated as point charges at their centers. Explain your work. So we can use a point where the graph crosses the x-axis. We can use such a point. For example, the graph is crossing the x-axis at x equals to 16. So at x equals to 16 centimeters, the value of E due to sphere A is the same as the value of E due to sphere B. And at this point, the resultant field strength is going to be equal to 0. At that point, the resultant value of E is 0. So we can equate the values of E. Remember, electric field strength is charge over 4 pi epsilon naught x squared. So we are going to equate. For A, sphere A, it will be the charge of sphere A divided by 4 pi epsilon naught time times the distance, which is going to be the distance of sphere A, which I will call it XA squared, which is 16. This should be equal to the charge of sphere B divided by 4 pi epsilon naught times the distance of sphere B from that point, which is going to be 24 minus 16. So when we combine this, we remain, of course, 4 pi epsilon naught has cancelled. So you have QA, which is 3.6 times 10 power negative 19 divided by XA, which is, I don't think I need to convert. I will not convert. But anyway, for clarity, let it be 0.16 squared. For QB, which is what we want to find, QB, divide by the distance. QB is going to be 24 minus 16 from the center, which is 8. So this is going to be 0.08 squared. Then you press your calculator, just cross multiply to find the QB, or the charge on sphere B. So I'm finding that the charge on sphere B is actually 9.0 times 10 power negative 10 coulombs. We can also try to see if we can use the charges on the surface. Let's see if we can use charge on the surface. I'll change the color. We can try to find the charges on each of the surfaces. So on the surface of sphere A, the value of E is 8 times 10 power 4. So we can say 8 times 8.0 times 10 power 4 is equal to Q, which is 3.6. No, but I just need to use this one alone. Let me use this one alone. On the surface of sphere B, I'll just be direct. E on the surface is 2 times 10 power times 10 power 4. That is E on the surface, which is this one. And this should be equal to the charge on the surface divided by 4 pi times epsilon naught, which is 8.85 times 10 power negative 12. Then times the radius is 2 times 10 power negative 2, and this is squared. We can try to check this if it gives us the same answer, because we want the charge on the sphere, so I can use its radius. So E is 2 point, so I have 2 exponent 4 times 4 pi times 8.85 exponent negative 12 times 2 exponent 2 exponent negative 2, and this is squared. So still QB is 8.896, which is 9.0, or you can take it to be 8.9 times 10 power negative 10 coulombs. That is, if I just consider the surface. Sphere B is removed. Use information from B to determine the electric potential on the surface of sphere A. Sphere B is removed. So we know that electric potential V is equal to charge divided by 4 pi epsilon naught times X. So I'll just say XA, QA, because I'm looking at the electric potential on the surface of sphere A. So we substitute. This is 3.6 times 10 power, and the charge is negative 9, divided by 4 pi times 8.85 times 10 power negative 12 times the radius of sphere A, which is 0.02 times 10 power negative 2. Alternatively, remember, instead of using the epsilon naught, I can also just always use K as 8.99 times 10 power 9 during calculation, because this is the same as 1 over 4 pi epsilon naught. So I'm pressing my calculator to find V. So finding V, it is giving me 1600 volts. Calculate the capacitance of a capacitor. By definition, capacitance is equal to charge over potential difference. So the charge is 3.6 times 10 power negative 19 divided by 1600. Pressing the calculator. Pressing the calculator is giving me 2.3 times 10 power negative 12 farads as the capacitance. Okay, I think I need to change the color. State what is meant by electric field. A field is a region of space where a force is experienced. Now, this is an electric field. So this is going to be a region of space. A region of space where a charge experiences an electric force. Region of space where a charge experiences an electric force, or a region of space where a force is experienced due to an electric charge. A region of space where a force is experienced due to a charge is what we call an electric field. Where a charge experiences an electric force is what we call an electric field. An isolated metal sphere has radius r, so this is radius. From 0 to r is radius. The charge is positive q. The electric field strength at its surface is E. So at the surface, electric field strength is E. Note that inside the conductor, E is going to be 0. I hope I have matched it very well. Okay. If at the surface it is E, inside it is 0. So we draw a horizontal line along the 0 axis. I mean the x axis, because inside E is 0. So I'll put my ruler is not stable, but I'll try. So there is a horizontal line along the x-axis. You use a ruler so that the line is very neat. So inside E is 0. Then I might draw a vertical line here along the surface. So I've drawn a vertical line along the surface. Okay, for you can put a ruler and draw a very neat line along the surface. Okay, then now let's see what happens outside the surface at 2r. Note that E is equal to a constant times Q over x squared or r squared. Let me just say x squared. So at 2r, E is going to be equal to K into, okay, KQ. E is going to be KQ, where there is x, I put there 2r, but remember it is squared. So this becomes a quarter of KQ over r, which is a quarter of E. So a quarter of E is 0.25. So it means I'm going to look for 0.25 at 2r. 0.25 is here. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 0.25 is there. At 3r, E is going to be KQ divided by 3r, and this is squared, which becomes 1 over 9 times E. This is E at, this was at 2r, this was at 3r. This was E at r is just E. Electric field strength at distance r. So this is 1 over 9 E. So I'll get the scale. The scale is 0.25 divided by 10, which is 0.025 for one small square. I want to plot 1 over 9 of E. So I will say 1 over 9 divided by 0.025 to get the number of small squares. 1 over 9 divided by 0.025. So this gives me 4.4, approximately 4 or 5 small squares from the base. So at 3r I have 1, 2, 3, 4. Around here, this is where we shall have our 1 over 9e. So we just draw now a smooth curve through these points. We draw a smooth curve through the points. It should be extremely smooth. So I will try my level best, but me I'm using it is on a computer. So for you can draw a better one. I don't know whether that is the best I can draw, but let me try to repeat again. So I'm trying to draw a better smooth curve. It is not easy, but I'll try. Yes. So you draw a very nice, it should not be a straight line, it should be a smooth curve going through those plotted points. Extremely smooth. So that will be our graph. It should not be a straight line. Please, it is not a straight line, it is a curve. Mine may not be look perfectly a curve as it would be on paper, but for you use a pencil and draw a very neat smooth curve. As simple as that. Part C, the sphere in B has a radius 0.26 meters. Electrical breakdown, that is a spark, occurs when the electric field strength at the surface of the sphere exceeds that. Determine the maximum charge that can be stored on the sphere before electrical breakdown occurs. So E is equal to Q divided by 4 pi epsilon naught x squared. So E should not exceed that, so I will simply say 2.0 times 10 power 6 is going to be equal to the charge divided by 4 pi times epsilon, which is 8.85 times 10 power negative 12. Then the radius is 0.26 squared. Pressing the calculator. So when I press my calculator, I arrive at 1.5 times 10 power negative 5 coulombs as the charge. It is 1.5. State what is meant by electric field strength. The force per unit charge acting on a positive charge. E is force per unit charge acting on a positive charge. This is very important. We always imagine a positive charge placed in the region of the electric field, and the force it experiences per unit charge is the electric field strength. Okay, next. 2-point charges A and B are situated a distance of 15 centimeters apart, as shown here. Point P lies on the line joining the charges and is a distance x from charge A. The variation with distance x of the electric field strength E at point P is shown here. By reference to the direction of the electric field, state and explain whether the charges A and B have the same or opposite signs. So you notice we said if they are like charges positive, positive, there is a point between them where E becomes 0, even if they are negative, negative. If they are unlike charges positive and negative, there is no such a point where E becomes 0. On this graph, you are seeing that there is a point where E becomes 0, so they are most likely going to be same sign because there is a point where E becomes 0. So we shall say they have same sign, they have same signs. The reason, there is a point between A and B, there is a point. There is a point between A and B where the field is 0. Or you could say the fields change direction between A and B. The fields change direction between A and B. Wrote in one of the questions we did, if they are unlike charges, the field does not change direction. It is always towards the negative. This one repels. Remember, we imagine a positive charge between them. The positive repels it towards the negative attracts it towards itself. For like charges, the field does not change direction. State why, although charge A is a point charge, the electric field strength between x equals 3 centimeters and x equals to 7 centimeters does not obey an inverse square law. They are saying although point charge A is a point charge, the electric field strength does not follow between x equals 3 and x equals to 7 does not follow the inverse square law. Yes, it is a point charge, but it's not the only charge there. It is a point charge, but it may not be the only charge there. There is also charge B, which is influencing the field. Therefore, we can say the field of charge A is also influenced by charge B. So, since charge A is not the only charge present, if it was the only charge present, then the electric field would perfectly follow the inverse square law. So we say the field of A is also influenced by charge B. So charge A is not isolated. Charge A is not isolated since it is not the only charge present. Charge A, we can't say charge A is not isolated since it is not the only charge present. The field, or we could even say that the resultant field is due to both charges, or the resultant field is due to both charges. So because it is not the only charge present, we can't consider it isolated, so the inverse square law will not apply. We could consider it isolated if it was extremely far from the other charge, so that the influence of the charge B is not experienced by charge A. Okay, use figure 5.2 to determine the ratio magnitude of charge A over magnitude of charge B. Magnitude of charge A over magnitude of charge B. We can use the surface, or we can even use the point where they meet at x equals 10 centimeters. I think that is the easiest. At x equals 10 centimeters, the resultant field is 0. So we know that E is equal to charge over 4 pi epsilon naught x squared. And we know that at x equals to 10 centimeters, E becomes 0, which means E due to A is 0 at 10 centimeters. So E due to A is the same as E due to B. So I'm substituting this expression. I'm substituting that expression. So it means Q for A over 4 pi epsilon naught x for A, distance of A from the center, which is 10 centimeters. That would be, I don't need to convert, but I can still convert, but it is useless because there I'm going to divide. So that is times 10 centimeters. Write this right very well. So this is 4 pi epsilon naught times 10 squared should be equal to Q at B, which is over 4 pi epsilon naught, the distance of B from, because this is the distance between the charges is 24, I mean it is 14, this is 10 centimeters, and this is 14, so I will say 14, actually it was 15. The distance between B and A was 15, so if at P where E is 0 is 10, so the other distance is 5, so it's not 14. So the other distance is 5 centimeters, 15 minus 10. So when you simplify this, remember you want QA divided by QB. 4 pi epsilon naught has cancelled. When I divide QA by QB, it becomes 10 squared divided by 5 squared, which is I think 40. No, 4.0, because it's 100 over 25. So this will be 4.0. We can also use E at the surface if we knew it. If we knew E at the surface, we could use it. But this is the easiest to use. Okay, again, what is meant by electric potential? Remember the work done per unit charge in moving a positive charge from infinity to the point. Work done per unit charge in moving a positive charge from infinity to from infinity to a point, or to the point. That is the work done to move a positive charge from infinity to the point. Two parallel metal plates A and B are held a distance d apart in a vacuum as illustrated here. Plate A is earthed, so it's at zero potential. Plate A is earthed and plate B is at potential of positive V naught. Point P is situated in the center region between the plates at a distance x from plate B. The potential at P is V. So this is potential there is V. On the figure, show the variation x with the potential V for values of x from x equals to 0 to x equals to d. So when x is measured from the upper plate, so when x is 0, I think V is going to be V naught. It means we shall be at the upper plate. So when x is 0, V should be V naught at the upper plate. And when x, this is a uniform field because these are parallel plates, it is a uniform field. That means acceleration is constant, the force is constant, so the velocity increases or decreases by equal amounts in equal time intervals. The potential difference, we know that E is equal to V over D, which means V is going to be directly proportional to distance. So it means as we move from the other, as we bring the plates closer to each other, or as we move from the other point to this point, V is going to be actually show the variation. The figure shows the variation x of the potential V for values of x from x equals to 0 to x equals to d. So we are starting from V naught because x is 0. So when we move point P, as we move point P from the upper plate towards the bottom plate, we are moving it towards a point where potential is 0. So it means the potential is going to decrease as we move from the upper plate to the one which is at Earth. When we are at Earth, when we are at the bottom plate, then the potential shall be at 0 potential, and the potential is going to decrease uniformly. So this is going to be a straight line. Potential, this is going to be a straight line. So I will try to draw a straight line between D and the V naught. I hope it works. hasn't worked. It hasn't worked very well. Okay, I think I've tried. So it will be a straight line with a negative gradient because as P moves on the top plate, P will be at potential V naught. On the bottom plate, P will be at zero potential. So that will be a straight line. That will be a straight line. Okay, part C. Two isolated metal spheres M and N, each of radius r, are situated in a vacuum. Their centers are at distance d as illustrated here. Each sphere has a charge positive q. Point P lies on the line joining the centers of the two spheres and is a distance y from the center of sphere M. On the figure 6.4 show the variation. The figure shows on figure 6.4 show the variation with distance y of the electric potential. Electric potential at a point P for values of y from 0 to y equals to d. Note that they are like charges. These are like charges, so potential is always positive. For like charges, the potential is always positive, so the graph will not go below the x-axis. That's number one. They are identical charges. That means the minimum potential will be at their midpoint. So we look for the midpoint. So this is 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. I think this is the midpoint, the center between the two charges. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah. So that is the midpoint between the charges. So this is where we expect to have our minimum potential. Since we don't have magnitude of charges, we shall just consider any value to be the minimum. Potential is maximum at the surface. They have the same radius, so it is going to be the same magnitude at the surface. So, and the potential at the surface is the same as the potential inside. Note that when E is 0 inside, then EV is constant inside and is the same as that on the surface. So inside, so here we have, this is the radius. So here along 0, between 0 and R, we draw a horizontal line. Using a ruler, you draw a horizontal line here, which is visible along the surface. Again, here inside the sphere, here we also draw a horizontal line. They have the same potential because they have the same magnitude of charge. Note that potential is equal to kq over r. They have the same magnitude of charge. They have the same radius. So inside the spheres, potential is constant and is the same as that on the surface. But as you move away from the surface, of course, potential decreases. As you move away from the surface, the potential decreases. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15. Okay, I think that is the center. So now it follows the inverse relationship, the reciprocal. So I will draw a curve. I will draw a curve with the minimum point there. This side I will also draw another curve. So for you can draw a better one, but that will be essentially that is the graph. It has a minimum point at a point between the two spheres at their center. That is going to be our graph. Minimum at the midpoint. It is minimum at the midpoint. V is always positive because they are both positive charges. Potential is always positive for positive charges. It will be negative for negative charges. However, it can be 0 if the charges are opposite in signs. There's a point where it can cross the x-axis. Okay. State what is meant by electric potential at a point, the work done per unit charge. The work done per unit charge in moving a positive charge. Moving a positive charge from infinity to the point. The work done per unit charge in moving a positive charge from infinity to the point, that is electric potential. The centers of two charged metal spheres A and B are separated by a distance 44.0 centimeters as shown here. A movable point P lies on the line joining the centers of the two spheres. Point P is a distance x from the center of sphere A. The variation with distance x of the electric potential V at a point P is shown here. The variation it is a graph of potential with the distance as shown here. So you see, we can even predict that actually the radius, because inside the conductor potential is constant and the same as the surface, we can predict actually that 10 point something, the scale here is I think 1, 2, 3, that is 1. So 12 centimeters is most likely going to be the radius. So the potential here is now decreasing to a minimum value at this point. Potential is minimum here. This is going to be 21, 22, 23, 24, 25, 26. That is at 26 centimeters. And then it is now increasing up to this point here. So the other one, we can even predict the radius of the other sphere. It is between this point and this point here. This is 41, 2, 3, 4, 44. And this is 32. 44 minus 32, it is still 12. Okay. Use the figure to state and explain whether the two spheres have charges of the same or opposite signs. You see that the potential is always positive. So the signs are the same potential. Because if the signs are the same, potential is the same. Potential is always positive, but the electric field strength changes direction. So these ones have the same sign. Same sign, reason, same sign of charge, since potential is always positive. Because potential is either positive or negative. So and it depends on the sign of the charge. So it is the same sign of charge since potential is always positive, or is always the same sign. The potential is always the same sign. We are saying it is positive because it's above the zero axis, the zero x-axis. So it is the same sign. Okay. A positively charged particle is at rest on the surface of sphere A. The particle moves freely from the surface of sphere A to the surface of sphere B. Describe qualitatively. Describe qualitatively. When they say qualitatively, it means we don't need to calculate anything. Describe qualitatively the variation, if any, with the distance x of the speed of the particle. First of all, we need to think backwards. We have been given the graph of electric field strength, a potential with distance, and we know electric field strength is directly proportional or is equal to the negative potential gradient. Electric field strength is the negative potential gradient. So that means electric field strength is going to be directly proportional to the gradient. And we know also that electric field strength is the force per unit charge, which is MA over charge, which means electric field strength is directly proportional to the acceleration. Electric field strength is directly proportional to the acceleration. If there is an acceleration, then the velocity is increasing or the speed is increasing. If the acceleration is positive, if E is positive, A is also positive. So this means an increase in speed. If E is negative, A is negative, which means a decrease in speed. So let's see. You are going to notice, because they told us the first part is between from x equals to 12 to x equals 25. So x equals to 12 is here and x equals 25. It's around the center. 1, 2, 3, 4, 5. It is here. Around x equals 25 centimeters. It is around here. So you are going to notice that between 12 and 25 centimeters, the gradient is negative itself. When we multiply by this negative, it means E is positive. Between 12 and 25, the gradient is negative, but remember E is the negative gradient, negative potential gradient. So it means if the gradient itself is negative, then times the negative, E becomes positive, which makes acceleration a positive. A positive acceleration means speed is increasing. At x equals 26 centimeters, you notice that the gradient here is going to be 0. Because you draw a tangent here, it will be a horizontal line at 26 centimeters. The gradient is 0, meaning the acceleration is 0. When the acceleration is 0, it means the speed is maximum and constant. Here the acceleration is 0, it means the speed is not changing. So it means we have reached maximum speed here. So speed is maximum at x equals 26 centimeters. Then after 26 centimeters, that is between 27 and 31, you see that the graph is going upwards, meaning the gradient is increasing. So the gradient is increasing and it is also positive. A positive gradient, when I multiply by this negative, it means E is now negative, which means the acceleration is now negative. A negative acceleration means a deceleration, so the speed is decreasing. And of course, after 30, at 32, the speed will still be just decreasing. It will still be decreasing. So we have seen now from x equals to 12 to x equals 25. I have explained how we see that the speed is increasing. So the speed increases. The speed increases, but it is increasing. When you look at the gradient here is actually, it is negative, but is decreasing. So it means the speed is increasing at a decreasing rate. At a decreasing rate, because the gradient is reducing, so the acceleration is reducing. Speed is increasing at a decreasing rate. Note that a decrease in acceleration does not mean slowing down. No. Think of a situation when if you were increasing the speed by 20 kilometers per hour and all of a sudden you start increasing it by just 10 kilometers per hour. The speed is still increasing, but at a decreasing rate because the acceleration is reducing. Then at x equals 26, we have seen the speed. We have seen at 26 centimeters, the tangent will be a horizontal line. The gradient is 0. It means E is 0 at that point. Acceleration is 0. When acceleration is 0, it means we have reached the maximum speed because the speed was increasing. So here speed is maximum. The speed is maximum. The acceleration is 0. E is 0. The speed is maximum. Then from 27 centimeters, from 27 to 31, we have seen the gradient is increasing, but because E is the negative gradient, E is going to be a negative, acceleration is a negative. But you see that the gradient is increasing at an increasing rate. So since the acceleration is negative, the speed is decreasing, but at an increasing rate because the gradient itself is increasing. So here we are saying the speed decreases, but at an increasing rate. Speed decreases at an increasing rate. Okay, so that is the question. Then, of course, at 32 centimeters, that is almost towards the surface, the speed is still increasing. That's all we can say. Speed is not increasing, decreasing. Speed is still decreasing. I know it is very hard for somebody to see that here the speed is decreasing, but remember, electric field strength is the negative potential gradient. The gradient at this point is increasing, but it is positive. When I multiply by this negative, E becomes negative. So the gradient is increasing, meaning that E is increasing, but negative. Acceleration, it is increasing in the opposite direction. Acceleration would be increasing in the opposite direction, where that would be a negative value, which means a deceleration. So a deceleration means speed is decreasing, but is decreasing rapidly because the graph is becoming steeper. Okay. Then next, the particle has charge 3.2 coulombs times 10 power negative 19 coulombs, and the mass is 6.6 times 10 power negative 27 kilograms. Calculate the maximum speed of the particle. So of course, as the particle is moving, the particle moves from surface A to surface B. There is a change in energy, work is done. The work done is going to be the gain or the when it loses kinetic energy, it must be gaining potential energy. So that means the work done is going to be charge times, of course, change in potential, which is going to be the same as a half mv squared. So we shall just substitute here. The charge is 3.2 times 10 power negative 19. The change in potential times 10 power negative 19 times the change in potential. Let's see the change in potential. So here it is on this surface. It is at, I think this is 2 point. The scale here is 0.2 divided by 10, which is 0.02. So we have 1, 2, 3, 4, 5, 6, 7. 7 times 0.02, that is 0.14. We add it to 2, so it becomes 2.14. So this is 2.14. And then at this level here, this is, I just subtract one small box. That would be 1 point, I think it's 1.4. No, we are interested in this point here. Because we want maximum speed is obtained at this point here. The speed has reached maximum. So this is in the middle of the box. So I think this is 1.43. Because one small square is 0.02, half a square is 0.01. So 1.42, 1.43. So we said it is from 2.14 and 1.43 to attain maximum speed times 10 power 4. And this is going to be equal to a half times 6.6 times 10 power negative 27 in kilograms times v squared. I will not make v the subject, I will just press my calculator. to get V squared. So making V squared the subject, I got V squared as 6.88 times 10 power 11, and when I find the square root, this is giving me 8.3 times 10 power 5 meters per second as the speed. State what is meant by electric field strength. Remember, is the force per unit, charge acting on a positive charge. The force per unit charge acting on a positive charge. Or you can simply say the force per unit positive charge, because you must refer to a positive charge. That is electric field strength. Okay. An isolated metal sphere A of radius 26 is positively charged. Sphere A is shown here. Electrical breakdown occurs when the electric field at the surface of the sphere exceeds this. Calculate the maximum charge. So we know that electric field strength should be Q divided by 4 pi epsilon naught times x squared. I will just use 1 over 4 pi epsilon naught as 8.99 times 10 power 9. So I'll simply say 2.0 times 10 power 4 is equal to 8.99 times 10 power 9. That is 1 over 4 pi epsilon naught. Then times Q divided by the radius is 26, which is 0.26 squared in meters. When I cross multiply, so my value of Q is 1.5 times 10 power negative 7 coulombs. The second isolated metal sphere B, also with the charge positive Q, has a radius of 52 centimeters. Calculate the additional charge in terms of Q that may be stored on the surface before electrical breakdown occurs. So for the first one, E, E was equal to the first charge. I'll just put there times K over the other one was 26. I will not change the units, 26 squared. For the second one, E is equal to K times the new value of charge. I'll call it charge B divided by, now the radius is 52 squared. So the value of E is going to be the same, because electrical breakdown occurs when the potential is, when the electric field strength exceeds 2.0 times 10 power 4. So I'm just going to divide these equations, or I'm going to equate them. So K QB over 52 squared is equal to KQ divided by 26 squared. So K cancels. So QB is going to be 52 squared divided by 26 squared times Q, the initial value of Q that we had. And you notice that QB is going to be equal to 4Q. So the question wants the additional charge added. So additional charge is going to be 4Q minus the initial value, which was Q. So additional charge is 3Q. It is 4Q, which we have got in the first case, minus Q, which we considered in the first case. 4Q in the second case minus Q, which is in the first case, that gives us 3Q as the additional charge. The electric potential is the work done per unit charge in moving a positive charge. The work done per unit charge. The work done per unit charge in moving unit in moving a positive charge. Positive charge from infinity to the point. The work done per unit charge in moving a positive charge from infinity to the point. That is electric potential. State the relationship between electric potential and electric field strength. We have all along been seeing that electric field strength is the negative potential gradient. So field strength is the negative potential gradient. Field strength equals to the negative potential gradient. Negative potential gradient. That is the relationship. So here we have two parallel metal plates. That means here the field is uniform. They are 1.2 centimeters apart. Plate A is earthed and plate B is at potential negative 75. A helium nucleus, that is He42. Charge is 2e, mass is 4u. Initially, the helium nucleus is at rest on plate A, okay, where x is 0. The helium nucleus is free to move between the plates. By considering energy changes of the helium nucleus, explain why the speed at which it reaches plate B is independent of the separation of the plates. So when it is moving from one plate to another plate, of course, as it gains kinetic energy, it loses potential energy. Because it's positively charged, moving from the bottom plate to the top plate, it is moving in the same direction as the field, so it is going to gain kinetic energy as it loses potential energy. So the gain in kinetic energy is going to be the loss in potential energy, which is actually the work done, which is equal to the work done. And of course, this will be a charge times potential difference, which will be Q times V. And QV is equal to simply a half mv squared. The loss in potential energy is equal to a half the gain kinetic energy, which is V squared. So you notice that in the expression there is no D. So we see that V is independent. V is independent. V is independent of the separation. V is independent of the separation because separation is not appearing. Separation is not in the expression. We see the separation is not in the expression, so V is independent of the separation. Okay. As the helium nucleus moves from plate A towards plate B, its distance x from plate A increases. Calculate the speed of the nucleus after it has moved a distance x equals to 0.4 centimeters from plate A. So it has moved a distance of 0.4 centimeters. They said as the helium nucleus moves from plate A towards plate B, its distance x from plate A increases. So we first of all find the potential at that distance. So at x equals to 0.40 centimeters, note that the total potential or the potential difference, this is the potential at x equals to 0 is 0, and the potential at x equals to 1.2 is 75 centimeters. That means the potential, we're now just going to use simple relationship. If at 1.2 centimeters the potential is negative 75, then at 0.4 centimeters, the potential will therefore be 0.4 divided by 1.2 times negative 75, which would be negative 25 volts. So the potential is negative 25 volts at 4 centimeters. So at x equals 0.4 centimeters, the potential is going to be negative 75 times 0.4 divided by 1.2, which gives us negative 25 volts. So remember, I have mv squared is equal to q times v. So we shall have a half times the mass. Remember, the mass was 4u for the helium nucleus, so that is 4 times 1.66 times 10 power negative 19 to change it from u to kilograms. Then times v squared will be equal to the charge of a helium nucleus is 2e, 2 times 1.6 times 10 power negative 19, then times the potential, which is 25. So I will just press my calculator, both sides. So this is giving me the speed as 4.9 times 10 power 4. Alternatively, you would first find the acceleration because the acceleration in a uniform field is going to be uniform. The acceleration, you can find acceleration. So acceleration is going to be that would be E over, it is to be QE over the mass, but E is V over D, so this will be Q V over MD. V is potential, so you get the acceleration. Since it is uniformly accelerated, now you can use V squared is equal to U squared plus 2AS. You have the acceleration, you have the distance. If it started from rest, then it becomes very easy. So it means V squared is going to be 2 times Q times V over MD, that is for the acceleration, then times the distance, which was 0.4 times 10 power negative 2. You can now just substitute 2 times the charge times, now this will be this potential between the plates, which is 75. The mass of the alpha particle times the distance d, which was between the plates. This one here, you consider the plates. V here it will be 75, and d here will be 1.2. Of course, you see we have now 0.4 divided by 1.2 times 75, which is the same as this part here, which is the same as that part. So it will give you the same answer as before. Okay. Two similar metal spheres A and B, each of radius r, are situated in a vacuum such that the separation of their centers is d, as shown here. The charges have the same polarity, positive, but the charge of sphere B is smaller than the charge of sphere A. The radii are the same. A movable point P is located on the line joining the centers of the two spheres. I want you to note that because the charges are not the same, it means the potential, if it is potential anyway, is going to be minimum closer to the smaller charge rather than to the larger charge. So if sphere B is smaller than sphere A, potential is minimum closer to sphere B rather than to sphere A. So on the figure, sketch a graph to show the variation with x of the electrical potential V between the centers of the two spheres. Remember, inside the sphere, potential is constant and is the same as the surface, as at the surface. Potential also depends on the magnitude of the charge because potential V is equal to Q times K over R. They have the same radii, but they don't have the same magnitude. Charge of sphere B is smaller, so potential of sphere B is going to be a smaller value on the surface compared to that one of sphere A. So we're now going to sketch the variation of potential with distance. So this side we have sphere A, and this is its surface. So potential on the surface of sphere A is going to be greater. Let me say it is here, and it is the same as the potential inside. So this will be a horizontal line as we have already seen before. This will be a horizontal line. You use a ruler and draw a very neat horizontal line here, which is visible by the examiner. Then potential on the surface of sphere B is also going to be constant and is the same as the potential inside, but note that sphere B has a smaller charge. So the potential here will be a value which is less than the one I've chosen in the first part. So it will be a horizontal line, but this line will be below the other one. And potential is minimum closer to the sphere B because it has a smaller charge. So I will choose a minimum point closer to the surface of sphere B. So let me say this point here. Now, as you move away from the surface, potential decreases. So I will do a smooth curve like this one for that one. Then I will also do a smooth curve. This should meet at the minimum point somewhere here. So all that is very important is to put the minimum point of these two graphs closer. The minimum point should be closer to the sphere with a smaller charge. I think I can draw something better than this. Yeah, something like that. The minimum point is going to be closer to the sphere with a smaller charge. As simple as that. Okay. I want this video to be exactly 2 hours. So we have 8 minutes. State one similarity and one difference between the electric field lines this time, and the gravitational field lines around an isolated positively charged metal sphere. If we consider its mass, the field is radial and towards the mass. If we consider its charge, the field is radial, but it is away from the charge. That is, so in both cases, the field lines are radial. The field lines are radial. That is a similarity. But the gravitational field lines will be towards the mass, towards the sphere. So gravitational field lines, the gravitational field lines are directed towards the sphere, and the electric field lines are directed away from the sphere. So if I consider a positive charge, specifically it was a positive charge. So the gravitational field lines are directed towards the sphere because the force is always attractive due to the mass. But if we consider the charge, field lines originate from positive, so the gravitational field lines are away from the sphere. A positive point charge Q is positioned at a fixed point X, and an additional positive point charge is positioned at a fixed point Y, as shown in the figure here. The distance between them is 2.5, 10 centimeters. They have like charges, so there is a neutral point in between them at a distance of 5 centimeters. At this point, E is 0, but V is not 0. V is just going to be twice. V is just going to be twice the potential of just due to 1. So points A and B are on this line XY. Point A is a distance 2.5 from X and point B is a distance 2.5 from Y. The electric field strength at point A is that. Note that to find electric field strength at a point, we imagine a positive charge there. We imagine a positive charge placed there. So we are imagining a positive charge of 1 coulomb placed at A. Note that Q is positive, it repels it to that side. So this is E due to A. Then this is E due to X, not due to A. Then due to Y, it is also going to repel to this side. So this will be E due to the charge at Y. Of course, E due to the charge at X is greater than E due to the charge at Y because X is closer to point A. But note that the resultant is 4.1. So we know that electric field strength is equal to Q divided by 4 pi epsilon naught times X squared. And the resultant will be E is going to be E due to X minus E due to Y. That will be the resultant. We subtract Y because E due to Y is weaker since the charge at Y is far from point A. So the resultant, remember, must be 4.1 times 10 power negative 5. So I'll simply say that 4.1 times 10 power negative 5 should be equal to the charge due to the charge at X divided by, why should I divide? I will just say times 8.99 times 10 power 9. That is for 1 over 4 pi epsilon naught. Divide by the distance, which is the distance is 0.025 squared minus the charge at Y, which is also Q, divided by, I will say just times 8.99 times 10 power 9 divided by the distance of the charge at Y from this, which is going to be 10 minus 2.5, which is 7.5. So that will be 0.075 squared. So I am just going to make Q the subject from my calculator. I know Q times 8.99 is a common factor, so I'll just get in the brackets 1 over 0.025 squared minus 0.075 squared, 1 over. I cross multiply, then I divide by 8.99 times 10 power 9. For you can make Q the subject whatever way you want. But me, when I simplify this, my calculator, there's only one unknown, so just make it the subject. Or you factor it out. Anyway, let me do this. 4.1 times 10 power negative 5 is equal to Q times 8.99 times 10 power 9 into brackets 1 over 0.025 squared minus 1 over 0.075 squared. This bracket you can put it in a calculator just at once. Then you get the answer you get. You just say 4.1 times 10 power negative 5 divide by that answer, also divide by 8.99 times 10 power 9. And this is giving me 3.2 times 10 power negative 8. On the figure, sketch the variation of the electric field strength E with distance D from A to B along the line. So we have seen that E is 0 at the center. From A to B, the distance is 5 centimeters, so E is 2.5. So E is going to be 0 at 1, 2, 3, 4, 5. The graph crosses the x-axis at that point. On the surface is 4.1. The scale here is 1 divided by 5, which is 0.2. So 4.1 is half a small square. This is 4.1 is somewhere here. It will also be 4.1 at the bottom. So 1, 2, 3, 4. Somewhere here, 4.1. Because changes direction. So E varies as the inverse square. E is inversely proportional to the square. So that is a curve. So here it is decreasing from 4.1 to goes to 0. And here it is increasing in the opposite direction up to negative 4.1 towards the other charge, like that. So that will be our graph. It should be a smooth curve. Here the gradient is decreasing to 0 because E reduces to 0. And here the gradient should be increasing in the opposite direction because there is a change in direction of the fields. A small positive charge is placed at A. The electric field causes this charge to move from rest along the line AB. Describe the acceleration of the charge as it moves from A to B. Here you see if we are moving from A, the value of E is decreasing. Note that E is force per unit charge, which is MA over charge. So E is decreasing, acceleration is decreasing from A to the center, to the midpoint. So E is decreasing, acceleration is decreasing. Then after, E is increasing but in the opposite direction, so it means the acceleration increases in the opposite direction. So we can say acceleration decreases to zero at the midpoint. Acceleration decreases to 0 at the midpoint, then it increases. Then it increases in the opposite direction. So here the gradient is, the electric field strength is increasing, you can see. So the acceleration must be increasing, but it is on the negative part, so it is increasing in the opposite direction. Okay, so that is solved past papers part 3. Watch out for part 4. Watch out for part 4.